Hello and welcome to Lab 6. So I've already got us set up here. This Excel file is within your lab. It's going to be linked in the question. So we're going to go through this real quick. Today for Lab 6, oh, I apologize for not being in my office. It's super hot in there. And so, yeah, I'm going to be a little more casual because I didn't want to sweat. Anyway, so today we're going to talk about HR diagram, which is a Hertzsprung-Russell diagram. It's two independent astronomers who came up with this technique of plotting a star's temperature against its luminosity. And so when they did that, they were able to discover some really interesting things. And just graphing it helped us to really understand more about how stars form and how they live. And how cool is that? A graph told us that. So don't ever like poo-poo algebra again, because it's really important. So anyway, all right, let me show you the graph. So basically, this is my crude attempt at creating an HR diagram. There you go. And so if you'll notice, we have four different color dots in here. There's blue dots, there's gray dots, there's yellow dots, and there's orange dots. Okay, so the blue dots are all actual stars. The yellow, orange, and gray, I made those up. Well, yeah, I put that data in. So if you'll notice here, we have the sun. The temperature is 5,800 Kelvin. The luminosity is 1. So all these numbers are compared to the sun. Alpha Centauri, same temperature, 5,800 Kelvin. The luminosity is 1.5, so that star is slightly brighter. Alpha Centauri B, 4,200 is the temperature, and the luminosity is 0.33, so it's only a third of our sun. And then Alpha Centauri C, 2,800 and 0.0001 luminosity. So you can barely see that puppy. Anyway, as we continue down here, there's 45, I think, stars. Here we got Sirius A star. Look, it's 23 times as bright as the sun. We got Vega, which is 55 times brighter than the sun. Beta Centauri. Yeah, anyway, so here we go. So all these numbers here, some of these are really big stars. And as I said, there's Rigel, and he's a big boy. Okay, so there's 45 blue stars. So if we examine the 45 blue stars again, oh, you should open your book to the HR diagram section. I can't remember which chapter that is. It's the one on stars. It might be chapter 9. Hold on. It might be 9 or 10. Anyway, okay. So if you'll notice here, there is sort of a pattern that you can see. So we've got this weird sort of swooshy up thing here. This is called the main sequence. So when a star is born, it is born with a specific mass, and that mass will determine where it lands on the main sequence. And it'll spend its whole life on the main sequence until it burns through its hydrogen, and then it'll go off the main sequence. And if you remember from the lecture or remember from looking at the book, hold on just a second. Remember, yeah, looking at the book, then you'll remember that the star turns off the main sequence and it comes back and it goes, yeah, it does a whole bunch of stuff. So down here we have white dwarfs. Up here we have red giants and supergiants. Okay, so those are actual real stars, the blue one. The sort of orange color here, I looked up the general characteristics of a white dwarf, of a supergiant, and then of a giant. So we got temperatures and luminosities here for each of these things. And so those are plotted on there. And then I started just like trying to come up with data, right? And so at first I thought I was going to make you guys, try to do something in this plot or something like that. And then I decided that was too complicated. So I just made up the data myself. So star 1, 2, and 3. So this is star 1 here with a luminosity of 0.01. Star 2 is 0.1 luminosity, and then star 3 is 1 luminosity. So those actually turned out to be really close to the main sequence. So I was just kind of guessing. I got temperatures 3,000, 4,000, 5,000, right? So it's not very complicated. But so these turned out to be pretty close to the main sequence. But then I decided to look at stars that would not be on the main sequence that we normally see. So we got star 4, 5, and 6. Those are in yellow. And so here is star, that is star 6, actually, with 2,500 Kelvin and 1 luminosity, so temperature or about as luminous as the sun. And then here's another one, star. This is star 5 with 22,000 Kelvin and 1 luminosity and 50,000 and 1 luminosity. So your question for this lab is, I would like you to think for a second. And I've got the main sequence, I've got white dwarfs, I've got red giants. Actually, you know what? I'm wondering if this data point is wrong. That would make this whole video, I would have to redo this whole video, and I don't want to. So anyway, I'm gonna, if it is wrong, I will put a note in the thing. So anyway, I'm thinking it should be closer down here. But that notwithstanding. So your question is, sorry, it's hot in my room as well. So my office is hot and my room is hot and whatever. Okay, so my question to you is, why can you not have a temperature that is super cold or super hot and maintain the same luminosity? Or conversely, you can sort of talk about why stars are sort of grouped into a similar temperature and luminosity scale. So it's a little bit out there. It's kind of a question that's going to require some thinking. If you are struggling with this, please email me and let's have a discussion, because this mode of teaching where we almost never interact is it's a little bit weird for a teacher, actually. So if you get to the point where this and you're like, I have absolutely no idea how to answer this question, let's have a little conversation and maybe we can get a little bit farther along. So once again, why is it not possible to have a similar luminosity to the sun, but have a super cold temperature or a super hot temperature? All right. Anyway, if you have any questions, like I said, let me know. Oh, just as a reminder, we do have observing opportunities coming up in the future. July 24th is the full moon. And if you're a member, if the weather would even cooperate, the goal there is to go out to a place, find out where it's going to rise, get there before it rises, and then watch it as it rises above the horizon. It's actually quite beautiful. You'll absolutely love it. Let's just hope that the weather holds out. Also, there is a meteor shower on July 28th and 29th. You can plan for that one, but sometimes sometimes they're really good shows and sometimes they're not that great shows, and sometimes you have to wait till 2 o'clock in the morning to see something. So anyway, and then also Saturn is at opposition on August 2nd, which means basically the sun is here, the earth is here, and then Saturn is directly behind us. And so it will be visible all night long. Which is kind of cool. I started to say one time, astronomers like it when things are next to each other in the sky. We also like it when one thing passes in front of another thing. We just think that's really awesome too. This is when I was talking about Mercury and catching Mercury, which I wasn't able to do because it was cloudy. So if you are also having trouble coming up with something for an observation report, also email me and maybe you can come up with some additional ideas for that. Okay, so if you have any questions, let me know, and I will talk to you soon. Have a fabulous day.